Que tá pensando ainda se ele quer gravar. Pronto. So, welcome everyone to the seminar from Probability Stochastic Process from IMI USP. And today we have with us Daniel Valesin from University of Groningen. So, welcome Daniel, and welcome.
Okay, thanks a lot for Aline for the introduction. Also, thank you very much for the invitation. It's a pleasure to give this talk. Of course, it would be even nicer to give a talk at USP. I'm from São Paulo originally, though I didn't study at USP. I did spend a few months there during the last year of my PhD. I spent some time in USP, and it was a pleasure to stay there. So I'll talk about some work that's been going on for a long time. So in fact, the first of this list I started already during my PhD, and the last one is from last year. So it's about, well, the contact process on certain random graphs. There will be two classes of random graphs that I'll talk about here. And so very briefly describe the contact process. I suppose many people in the audience are already familiar with it. So the contact process is, so we fix a graph, which is wrong color, I guess. Let's say we fix a graph G, which can assume is a locally finite and connected graph. For most of this talk, it will be even a finite graph. And the contact process is a continuous time Markov process on the state space 0, 1 to the vertices of the graph. And the usual interpretation is that, well, this is a model for epidemics. 0 means that vertex is healthy, and 1 means that the vertex is infected. And so the model has a parameter lambda larger than 0. This is called the infection rate. And the dynamics is given by the following rules. So the jump rates from a configuration, so from configuration psi in the state space, and at a fixed vertex, so at x belonging to V, are as follows. So you go from infected to healthy spontaneously with rate 1, and you go from healthy to infected with a rate that is equal to lambda times the number of infected neighbors, so number of y neighboring this site x, so that psi of y is 1. So this is the dynamics, and the usual notation that is employed. Notation is that we write something like this: psi superscript a t. So t is time, and a here is a subset of the vertices, and it's the set of initially infected. So vertices that are infected at time 0. And that's one notation that's commonly used. Another thing is I'll write 0 with an underline. This is also configuration, and it denotes the all healthy configuration. So when everybody is in state 0, and it's very easy to see from the description I gave above that this is an absorbing state for the contact process dynamics. So it's a trap state. Once it's reached, the dynamics stays here. And one observation I want to make right away is that when the graph is finite, then this absorbing state is reached almost surely at some point in time, almost surely. And because of that, well, so we can define this random variable denoted tau g, the graph, which is the first time. So the time it takes for this trapped state to be reached. So infimum of t, so that psi vt is equal to 0. And so this is a stopping time, a random variable, and it's called the extinction time of the infection. So it's not well, it's the time it takes for the infection to die. The population itself doesn't die, so it just gets sick and healthy. It's the time it takes for the infection to die. And
Daniel?
Yes.
We have a question. We need to assume lambda less than 1, right? Smaller than 1.
Lambda is any positive real number. You mean, so is it for this? Is that the question?
Can I reformulate?
Sorry?
Yeah. The question is about this. This is also is always true for any choice of lambda, that you are going to reach 0?
It's true for any choice of lambda, at least if the graph is finite, because if the graph is finite, you know, you can look at the dynamics and you can look at time intervals of, let's say, 1 second. And you can consider every 1 second, there is a chance that everybody who is sick gets better and nobody transmits the disease. So this has a positive probability, and it will eventually occur. And when it occurs, the infection is gone.
Okay,
so,
thank you, Daniel.
Sure. So this is extinction time. So it's almost surely finite random variable as on a finite graph. So let me say a few words about what is understood by metastability for the contact process. And so the framework for the study of metastability for contact process is usually as follows. We fix some value of the infection rate, so lambda larger than 0. And we also fix a sequence of graphs, Gn, with number of vertices. So this for me is a number of vertices going to infinity. And then, so typically this sequence of graphs is, well, from some natural choice, like boxes of the lattice or some random graph model. And then we study this stopping time, this extinction time. So fixed lambda and taking the graph, the size of the graph to infinity, and we study the way this random variable typically grows. One thing I wanted to emphasize and forgot is that for the study of the extinction time, I will always start the dynamics from everybody infected. So I start at time 0 with everybody infected and wait until the infection is gone. Okay, so this is a framework for metastability, and let me give one example of a situation where metastability occurs. So let's say we take Gn to be boxes of Zd, so 1 and to the D with the nearest neighbor edges, so box of lattice. And then there's well-known, well-known statement that there is a critical value lambda c larger than 0, so that the following thing happens. So if lambda is smaller than lambda c, then the extinction time is very small. So it's of order logarithmic, log of the volume of the graph, log of n. Whereas if lambda is larger than lambda c, then tau of Gn is like exponential, and then some constant times the volume of the graph. And by the way, for people who know, this lambda c is the same lambda c that appears in the infinite volume phase transition. So when you study the contact process on Zd, this is the lambda c that is a critical value for the contact process on Zd, but I will not need to talk about this. So just talking about finite volume. So this here, this second regime here is the metastable regime. Well, it's called a metastable regime because it's a regime where the process stays for a very long time in a situation that resembles an equilibrium. where the infection is active and spreading around, this takes very long, exponential in the volume of the graph, until it eventually goes to the real equilibrium, which is this configuration. I should also mention that this result that I'm stating here for boxes, so this what I wrote, is was proved by several people. In particular, the supercritical part, a version of this was first proved by Cassandra Galvis, Olivieri, and Baris. Maria Eulalia is in the audience. So they proved that, I hope not to make a mistake here, but in dimension 1 and for lambda sufficiently large. And then the result was improved in steps until eventually the form that I'm giving here. So Roberto Schonman worked on it, Duret and Schonman also worked on it. The version that is written here was proved by Tom Mountford. And the subcritical one was proved by Duret and Liu, I believe. So this is the metastable regime that I will be mostly interested in for today. And so this was the beginnings of the study of the contact process on finite graphs. And in the 2000s, there was somewhat of a shift of interests. Namely, people started studying the contact process on random graphs. And in particular for metastability, a phenomenon was recognized. And I'm going to summarize like this. On a scale-free graphs, lambda c is equal to 0. So what I mean by lambda c is equal to 0 on scale-free, well, what I mean by scale-free graphs, that means just graphs where the degree distribution is a power law. But more importantly, what I mean by lambda c equal to 0 is that this first regime here does not occur. So the infection stays alive in the graph for a very long time, even if lambda is very close to 0. So even when lambda small, arbitrarily small, tau of Gn grows rapidly. So you always have this metastable regime on power law random graphs. And the reason for this phenomenon is that if you have a power law, so if you have a vertex of high degree, so let's say this is a vertex of degree d, suppose that d is large. So on this vertex, so if d is large, what happens is that if the center of this star graph is infected, then immediately it sends the infection to many neighbors. And then the infection keeps coming back to the center. So this star alone will sustain the infection for a very long time. So the process survives on this, for a time, which is about exponential of some constant times lambda squared times this degree. So this is true for lambda small. This is true for lambda smaller than 1. And because of this, when the degree is much larger than 1 over lambda squared, well, you have survival for a long time in this star. And then when you have a power law graph, a graph, so let's say here you have Gn, which is a graph where the degree distribution is a power law. So in fact, you will find many of these stars with degree larger than 1 over lambda squared, and they will not be, or depends a bit on the specificities of the graph, but typically they will be close to each other, these vertices of degree. So what you do then is you find a subgraph of Gn, find a subgraph which contains basically these stars, and if you can guarantee that they're close to each other, then the infection can sustain itself just from star to star. So it will be present in each star, and even if it vanishes from one of the stars, it will arrive back from some other stuff. So that was the picture that justifies this sentence here. And so I want to talk about some results along these lines. So now let me go to part 2 of the talk, which is where I'll describe the random graphs that I will be interested in. So the first one I will describe very quickly because I think most people will already be familiar with it. So this is the configuration model. So the configuration model is random graph with a prescribed degree distribution. So you define it as follows. So you start with, let's say P is probability on the natural numbers, probability on N. And let's assume, yeah, I'll make the following assumption. Assume that P of 1 and 2 is equal to 0. So P is supported on 3 or more. And this P will be the degree distribution of the graph. The only reason I make this assumption here is that I want to, this assumption is a cheap way to guarantee that you get a connected graph with high probability. But it's not terribly important that you assume this. And you also fix a natural number n, which will be number of vertices. And then with these two ingredients, P and N, you define the graph as follows. First, you sample a sequence, D1 ... Dn. So this is IID with distribution P, but conditioned on the sum being even. So conditioned on the event that the sum of di is even. So first you do this, and then you draw a picture. Once you have these random variables, you draw the following picture. You put the vertices here, so vertex 1, vertex 2, and you give each vertex, so vertex 1, D1 half edges. So this is 1/2 of an edge. You give D2, you give vertex 2, D2 half edges, and so on. And then because you're conditioning on this event, there is at least one way to match the half edges in order to take a perfect matching of the half edges in order to construct a graph out of this. So I could, for example, take this one with this one, then this one with this one, some procedure. So there's at least one way to do this. And what we do is that we construct a graph out of this picture uniformly at random among all the possible ways to do that. So match half edges uniformly at random, and you get like that random graph, which I would denote well, random graph Gn. Later, I'll also assume that the degree distribution is a power law, so that indeed we get a power law random graph. So that's the configuration model. As I said, it was a quick introduction. Now the second class of graphs that I'll talk about is, I'll spend more time because I guess it will be less familiar. So this is called, well, it's certainly less familiar to me because I just became acquainted with this hyperbolic. So I just became acquainted with these graphs maybe 1.5 years ago or 2 years ago. So this is a model of random graphs in hyperbolic space, which to me sounds quite intimidating because I don't know anything about hyperbolic geometry. So I just take this as a model of random graphs. So I'll tell you about this graph, what I know about it, and what will be important for this talk. But if you have questions about hyperbolic geometry, you put me in a tight spot. But this class of random graphs was introduced by several people. So Kryukov, Papadopoulos, Kitsak, Vadat, and Bogunya. Let me not write the list of names. And 2010. And the motivation for the definition of these random graphs is that they capture three three features that are sort of the holy trinity of complex networks. So they exhibit a small world phenomenon, meaning that well, vertices are typically close to each other, diameter is small. Well, they are scale-free, meaning a power law degree distribution, and also they exhibit clustering. So clustering meaning that if you have two friends, typically they are all, well, they have a good chance of also being friends with themselves. So there is some density of triangles. So the graph locally does not look like a tree. So this, yeah, so these people introduced this graph because it captured this property, and the intuition behind it is that well, real-world networks, they should they sometimes reflect a certain hidden geometry. Like you can think of vertices as being positioned in some sort of space. And if that were the case, then this geometry should be hyperbolic geometry, because many complex networks have a hierarchical structure, and hyperbolic geometry has this feature. But okay, let me give you the definition of the graph. And so there will be now two parameters. There will be n natural, which is again number of vertices, or at least expected number of vertices. The actual number of vertices will be random. And there will be also a parameter alpha larger than 0, and I'll explain the role of this alpha in a bit. For people who have seen this graph before, they may also notice that in the literature there is a further parameter called eta. And here I won't take this parameter eta, or actually I'll take it equal to 1 everywhere, which means that I will omit it. So for me, only these two parameters, n and alpha, will be present. So here's how I define the graph. I start with a two-dimensional disk of radius r. I could write rn, which is 2 log n. So a disk of radius log n, and disks of points of the disk. I'll denote points of the disk through polar coordinates. So r and theta, with r between 0 and big R, and theta between 1 and 2 pi. And so I start by, so I want to construct a random graph. And I start by sampling the set of vertices of the graph. So the vertices, I will call this a set of vertices Vn. And I take them as a Poisson point process on the disk, on this two-dimensional disk. But it won't be with the Lebesgue measure as the intensity function. Rather, it will be with an intensity function that I'll tell you now. Intensity function as follows. So there will be a function g of r and theta. And g of r and theta is just a constant depending on the parameter alpha times hyperbolic sine of alpha times r. And this constant C alpha chosen, I forgot to write the explicit value of C alpha, but it's really not important. So chosen so that the integral on the disk of this function g, the theta, is well, yeah, the integral on the disk of g is equal to n, so that you know, you make a Poisson point process with an intensity function whose integral is this. So that means that n is then equal to the expectation of the number of vertices. That's the integral of the function. And so the hyperbolic sine. So this the value of alpha here, it controls the distribution of points. So alpha controls how points are typically distributed. So there are always typically n points. So the number of points is a Poisson random variable with parameter n. But alpha controls how much the points are concentrated on the boundary. So somehow, if you take alpha to 0, you get closer and closer to uniform distribution on the disk, Lebesgue measure, as if the Lebesgue measure were the intensity. Whereas if you take alpha to infinity, well, the larger you take alpha, the more points will tend to be close to the boundary. And in the center, it will be very rare. So if alpha is to infinity, if you take it to infinity, you would get uniform distribution on the circumference on boundary. So all the vertices would be in the circumference. So this is how you sample the vertices. And now let me tell you how you put the edges. So the edges, you put them deterministically. So put edge between, let's say u, which is RU theta u, and u prime. If they are close to each other, so if well, hyperbolic distance, so distance hyperbolic between u and u prime is less than or equal to r, where well, hyperbolic distance, I will write here what is the expression that I'm taking for hyperbolic distance, but again, it will not be very important for the rest. So I'll just write the expression because I would feel bad about not giving an actual definition, but it will look ugly and long, but please feel free to ignore this expression. So take cosine hyperbolic of one of them, the other one, and then minus the product of the hyperbolic sines. And then here times still the cosine of the difference between the angles, and here this is wrapped around in the circle. So this is the expression for the distance, or at least it's implicitly defined. So if you want the distance, you have to take arc hyperbolic cosine of the right-hand side. But what is important, so let me tell you what the balls look like. So balls of radius r in this norm, because well, you put an edge between 2 points if they are one inside the ball of radius r of the other. So the balls, they look like this. If you take a point, so if you take a point very near the center of the circle, then the ball will contain almost the whole thing. And in fact, if it would happen that in the Poisson process you would get a point exactly in the circle, then the ball of radius r would be the whole disk. Yeah. So if you're here, then it looks sort of like this. But as you approach the boundary, then it gets kind of this thin thing in the boundary, and it gets larger here. So that's to say that if you have points in the boundary, then you will only put an edge between them if they're very close to each other. But if there is a point near the center, then it will be connected to almost to lots of people in the boundary and all around. So the vertices that are near the center, they tend to have high degree, and vertices near the boundary tend to have order 1 degree. So that's the graph, and I won't say too much about it because I want to get back to the contact process. But I do need to mention one thing, or a couple things. So what is one thing that is known and is important to mention is that the degree distribution in this graph, so the degrees follow a power law with exponent 2 alpha plus 1. And what I mean by this is that the probability that the degree of a vertex chosen uniformly at random being around k, this will be around k to the minus 2 alpha plus 1. So this was recognized by the people who defined the graph. So this is one thing I want to mention. The other thing I want to mention about this graph, and this was proved by Bode, Fontolakis, and Müller, So there are two papers, 15 and 16. And they prove that this parameter alpha, so when alpha is less than 1, then there is unique, with high probability that there is a, with high probability there is a unique linear sized component, meaning a connected component with order n vertices, and then all the other components are sublinear size with high probability. Whereas if alpha is larger than 1, then already the largest component is sublinear size, so much smaller than n. Well, they know the exponent. The exponent is it's n to the 1 over 2 alpha, if alpha is more than 1. So okay, so these are the two graphs that I'll take, the configuration model and this random hyperbolic graph. So now let me tell you the results that we found for results. So of course the plan is to study the contact process on these graphs. And well, the reason we study the contact process on these graphs is, of course, that if we're interested in a model spread of an infection, then we want to also make the infection spread in a network that resembles real-world networks. So, of course, it's nice to study the contact process on lattices, but well, it's also important to understand it in networks that capture aspects of real-world biological and social networks. So for what follows, GN for me will be either the configuration model with P degree distribution, P, which is a power law. So it has polynomial decay. So power law with exponent, which I will call A. Exponent A, and I will assume that this A is larger than 2. And this is to ensure that I have finite expectation for the degree distribution. So what I mean by power law with exponent A larger than 2 is that P of k is approximately, well, k to, well, maybe some constant, but k to the minus A. So Gn is either this or the random hyperbolic graph that I presented, with the parameter alpha will be between 1/2, so 1/2 smaller than alpha, smaller than 1. So this means, so if you remember up here, I told you that the degree distribution here is a power law with exponent 2 alpha plus 1. So if I take alpha between 1/2 and 1, so this means that 2 alpha plus 1 will be between 2 and 3. And well, the reason I want it to be less than 1 is that I want a linear sized component. So I want a connected component of order n, because I want to run the contact process on the graph, and it's not so much. It would be a bit tricky to if the graph has many small components of order well, sublinear in n. So I'm interested in cases where there's a giant component, and this restriction I make also because I want finite expectation of the degree distribution. So yeah, but in any case, so let me emphasize, for the configuration model, this A will be the power law exponent. And for the random hyperbolic graph, I'm going to call this thing here A. So in both cases, I will call A the power law exponent, except that in the configuration model, A comes directly from the degree distribution, And in the random hyperbolic graph, well, A is this function of the parameter alpha, which regulates the distribution of vertices in the graph. Okay, so yeah, but in both cases, A is the parallel exponent. And what we want to do now is, as in the beginning of the talk, we want to fix lambda larger than 0 and run contact process with parameter lambda on Gn on the graph. In either case, on Gn. Started from all infected, always, and study the extinction time of the infection. So, okay, so I'll state the first result. So, theorem 1. Okay, so this is, let me call this the persistence theorem. And this is, okay, for the configuration model, it was proved by Mountford, Mourrat, myself, and Qiang. And for the hyperbolic graph by Linker, Mitsche, Schapira, and myself. So the statement is that for any lambda larger than 0, there exists C larger than 0, so that the probability for process on Gn that the extinction time, tau of Gn, is more than exponential C lambda times n, that this goes to 1 as n goes to infinity. So this is the result that I announced in the beginning, that you survive for a long time, even if the infection rate is very small. Let me also mention that for the case of the configuration model, a weaker result was already known due to Chatterjee and Duret. They had already proved that this was at least a stretched exponential function, so n to the power of beta for some beta smaller than 1. So we improved their results to get the exponential time. So that's the first theorem. So it's very easy to understand the statement. So now the second theorem has a much more subtle statement, and it gives the title of this talk. So this is about densities, or metastable density. So it goes as follows. For any lambda larger than 0, and also for any sequence of times, so any sequence Tn with Tn going to infinity, but slower than exponentially. So slower than exponentially, that means that log of Tn divided by n goes to 0 as n goes to infinity. So for any lambda and for any sequence of times like this, the following thing holds. So we have that the probability. So the probability for the process on the graph with n vertices, on average n vertices. So I start the process with everybody infected at time 0, and I run the infection up to time Tn. So the choice of this Tn, so Tn is supposed to be a typical time of activity of the infection. Why do I call it a typical time typical time on Gn? Because, you know, I'm taking Tn to infinity. So if you look at the process on Gn, that means that you gave the process some time for mixing, because you start from everybody infected, but you run the dynamics for a long time. But smaller than exponentially, so this means that Tn will be much smaller than the extinction time of the infection. So it's like you take a snapshot of the process at time Tn. So here you look at the number of infected and divide by n. So this is indeed a density. And then the claim is that this will be close to a certain function, which I will call gamma of lambda. So the probability that this is larger than epsilon goes to 0 as n goes to infinity. And now I have to tell you what gamma is. So where, and this is for every epsilon. So okay, with high probability, the density, which is a random quantity, will be close to a certain deterministic function of lambda. and gamma of lambda. And gamma of lambda is a function that is model dependent, or model, meaning that it may be a different function for the configuration model and for the random hyperbolic graph, but it has some universality aspect for these two models, namely, so goes as follows. So gamma of lambda, if I take lambda to 0, so what's happening here? So when I take lambda to 0, it's well, the infection rate is being taken to 0, so I'm looking at the aspect that this predicted value for the density has when the infection rate is very small. So this has 3 shapes depending on the value of the power law exponent in the degree distribution. So when A is between 2 and 2.5, 5 over 2, it's the value is lambda to the power of 1 over 3 minus A. When A is between 5 over 2 and 3, then it changes to being lambda to the power of 2A minus 3 divided by log of 1 over lambda to the power of A minus 2. A minus 2. And when A is larger than 3, then it's well, the same thing, except that the denominator has a power of log 1 over lambda to the power of 2A minus 4. So that's it. And let me remind you, for the two models I'm considering, so for the configuration model, I'm taking any A larger than 2, but for the hyperbolic graph, I'm just taking A between 2 and 3. So in this result, these 2 are for the hyperbolic graph, hyperbolic graph, and whereas the 3 are applicable to the configuration model. So yeah, as I said, this is about the density when the infection rate is very small, and we see these numbers here as a sort of critical exponents because, as I told you, the idea is that lambda c is equal to 0 for this graph. So when you take lambda to 0 and you look at the exponent of this density, it's something like looking at a critical exponent. But yeah, what I find most interesting about this result is that the same exponents appear in these two models. And so these are the two results I wanted to tell you about. Oh yeah, and by the way, this the density result was proved for the configuration model by Mountford, myself, and Yao. I think it's 13. And the hyperbolic graph is this same paper, Linker, Mitsche, Schapira, and myself. So let me say a few words now about, not much, but let me just make some comments about proofs. So I told you two theorems. So for the persistence theorem, I won't say too much persistence theorem. I already more or less showed you in the beginning how the proof of these things go. So you have the graph Gn, and the game is finding a certain subgraph consisting of stars and line segments. So what you need to do is find the subgraph, and it's important that it has order n stars, because somehow these stars they do the heavy lifting in maintaining the infection. So you should consider this when you see this subgraph. You should think of it as a collapsed. So you should think that each star is collapsed into a vertex, and the segments connecting the stars are collapsed into edges. So it's like you have a coarse-grained contact process happening on this rescaled on this other graph, on this collapsed graph. So that's the philosophy of this proof, and the challenge is well, finding this this subgraph in the two cases, but that's something about the graph and not about the contact process. But let me say a little bit more about the density theorem. So the density. So for the density theorem, we want to study, well, this is the quantity that I wrote, which is psi Vn at the typical time Tn divided by n. So that's the density. And in order to study this quantity, it's you can reduce the study of this quantity to the study of this quantity instead. So you take the contact process on the graph, start from everybody infected, run it up to time n. But instead of looking at a density, you look at the probability that a uniformly chosen vertex, so uniformly at random. So U is a vertex chosen uniformly at random, and you look at the probability that it's infected. So the first step in the argument is to reduce the study of the density to the study of this thing, which is well, pretty clear that this should be the case. The second step is to use a property of the contact process called duality that many of you may be familiar with, but I won't explain here. But what duality gives is that, so here we start from everybody infected at time 0, and we look at U being infected at time Tn, and it turns out that this is the same as gives the same probability as starting from only U infected at time 0 and looking at the probability that the event that you are not dead at time Tn. So if you haven't seen anything like this before, I'll ask you to believe this part. This is just one of the most well-known properties of the contact process. Actually, it's self-duality that I should say. And finally, the most important part. So this up to here, it's absolutely classical and well-known things about the contact process. But now the important thing is that when you take n to infinity, there's a probability, when you start from a uniformly chosen vertex and you want to know if you're alive at time Tn, then you know uniformly chosen vertex, then it starts to matter what the graph looks like locally, so the local limit of the graph. And that's what we get now. So the probability. So now on another graph, and this will be an infinite graph, which I will denote by G infinity, and it has a root O. So this is an infinite random rooted graph. So you have a certain random rooted graph, and you look at the probability that the contact process started from only the root infected survives forever. So different from 0 for every t. So we replace the Tn here by surviving forever here. So this is the strategy is to reduce the study of the density to the study of the survival probability of the contact process on a certain infinite random graph. And what is this infinite random graph? It depends on the two models. So in case of the configuration model, this is a Galton-Watson tree. Well, so it has a root. It's a Galton-Watson tree. The offspring distribution for the root, so you have O. The offspring distribution for the root is P. But then for the rest of the tree, it's the size biased version of P. Version of P. So it's like a two-stage Galton-Watson tree. And for the random hyperbolic graph, it's a certain random graph that has been well, introduced by the authors that I mentioned earlier. But it's a random graph that is embedded in the half space, so in two-dimensional half space, so like this. So it's a random graph, a rooted random graph that is embedded here. And it's the reason that you get a half space like this is that you should imagine that you have the random hyperbolic graph, and you're choosing a point uniformly at random. So typically you choose a point near the boundary. So somehow the boundary here corresponds to the half space here, and then you get a random graph around that. The difference between these two settings is that, well, here you get something that is a tree, and here you get something that is not a tree locally. As I said, this graph exhibits clustering, so proving the result here is a bit more technical, required some new ideas. Last thing I want to say, I guess I'm running out of time, but last thing I want to say is that if you're studying this this quantity, so once more, I've said it many times, we're taking lambda very small, so small infection rate, and we're looking at the event that the infection survives on this graph. So the infection survives forever, even though lambda is very small. So what is written here is a very rare event. It's an event with extremely small probability, and you're taking lambda to 0. So, estimating this probability has a bit of a flavor of large deviation theory, because somehow you have to find the best strategy for the infection to survive. So if it wants to survive, that's a rare occurrence, and it has to find somehow the most likely way in which it does that. And let me mention now that these 3 regimes that appear here, they have to do with different strategies for this infection, for the infection to survive. And in these two first ones, it's the same strategy for the 2 graphs. So you see the universality not only in the exponent, but also in the description of what's happening locally with the infection. But okay, I think I've said more or less everything I wanted to say. If there are questions, well, about any part of this, I'll be happy to do my best to answer. So thank you very much.
Do we have questions or comments? Maria Wale, please.
So, thanks a lot, Daniel, for this great talk.
Thanks.
One something that occurs to me, but I don't know if I understood properly. In this result about the density, so you have Tn is a sequence that's given, and then there is an estimate in probability. The probability goes to 0. Does it make sense? Can you do something that controls the time stability of your density for a while? So I don't want only to look at a given time, but I want to give more, not only that the probability goes to 0, but to say something that...
Okay, I see. Okay, so thanks for the question. Let me just fix this very quickly. I realized I should have written this instead. When you asked your question, I realized this. So this function is within constants of this. But okay, let me see if I can answer that. One thing that we could do without much more difficulty is if you have not one time, but you have a bunch of times, let's say Tn1 less than Tn2 less than ... Tn, and here you could even allow it to depend on n, but let's say in a way that the difference between them goes to infinity. So that I think would not give any additional problem. That would be fine. But if you're really interested in looking at the whole trajectory of the process and looking at moments when it deviates from this density, then I can say really nothing at all. Then it's much harder than everything that I'm talking about here. Yeah. Because all I can do is this kind of simple duality argument. You take 1 point or maybe 2 points and draw them backwards in time.
Yeah, I see. And about the time, the persistence, the time, is there something about the asymptotic distribution of the time, if you normalize time? That if it is exponential or if there is something else.
Okay, I didn't mention that, but I don't remember if we write this in the paper, or maybe we write it in one of the papers. But I think it's not from known techniques. It's not too difficult to prove that if you're normalized by expectation, it will converge to exponential distribution with parameter 1.
Thank you. Mm-hmm. Thank you. Thank you. Thank you.
Thanks.
Do we have any more questions or comments?
Yes, I can. Okay.
Yeah, sure.
Can I make a question? Yes. Can you hear me?
Yes.
Yes.
Okay. So since Eulalia asked twice, so I'll pose 2 questions if I may. I mean, I can make one and then wait for the second one. So first one is I mean, your Tn is sub-exponential, but I mean, you have an exponential time to survive, right? So
yes.
What can you expect for short exponential times?
Okay, yeah. So this is mostly me being. So if you here take Tn much smaller. Oh, can you still hear me?
Yeah, sure.
Okay. So if you take Tn like this, where this C lambda is the constant of the constant of the persistence. So it's this C lambda. Then I expect so this would also work.
Great.
Yeah, so of course this C lambda is just a lower bound for the extinction time, but if you take any exponential function that is actually smaller than the constant that appears in this lower bound, it would also be perfectly fine.
Great.
Yeah, of course we don't know well anything more precise here, so I wouldn't be able to say anything more precise about which Tn you can take, but yeah, if you take exponential and not that fast, then it would also be fine.
Okay, and the other one, if I may, is about the. I mean, you have a result for the density. Can you say anything about the configurational limit, or I know it's perhaps I don't know. Yeah.
Yes. So let's. I guess. Do you mean by that? Suppose that you take, because the density is like you sample a point, a vertex uniformly at random, and you ask, is it infected or not? But you could instead look at a ball around this vertex and look at the distribution there, right?
Yeah.
So you could do that, and so if you do that with a ball of fixed radius, so you don't take the radius, don't make the radius grow also with the size of the graph, then I think the same duality considerations would show that. Let me make sure that I'm not saying anything stupid here. Oh no, that's a bit trickier, I guess. Yeah. So my guess is that it should give the stationary distribution of the contact process on the limiting graph. Do you see what I mean? So you take this,
yeah.
So you have the local graph limit, and you have the upper stationary distribution of the contact process there, and you would see that there. And I guess the duality argument would also show this, but I'm not completely sure now.
Okay, thank you.
Yeah, thanks, Anata.
Do we have any other questions or comments? If not, let's thanks Daniel again. Thank you, Daniel.
Okay. Thanks a lot. It was my pleasure.